Section 4.1 again. How to locate extreme values. Have a review first. Number 1, terminologies. A. In this book, a maximum value means a global maximum value or an absolute maximum value. These three terms, they mean the same thing. Similarly, a minimum value means a global minimum value or an absolute minimum value. B. A global maximum value or a global minimum value is called an extreme value. So, an extreme value is either a global maximum value or a global minimum value. C. A local maximum value or a local minimum value is called a local extreme value. Review number 2. This is a convention. A local maximum value or a local minimum value occurs only at a point inside the interval. For example, if a local maximum value occurs at one endpoint of the interval of interest, then the book doesn't consider it as a local maximum. Similarly, a local minimum value, if it occurs at an endpoint of the interval, the book doesn't count it as a local minimum. Review number 3. Whether or not a continuous function has a maximum value or a minimum value depends on the interval of interest. This is a calculus language. In geometrical language, in graphical language, it is whether or not a continuous curve, a function is a curve, whether or not a continuous curve has a highest point maximum value or a lowest point minimum value depends on the interval of interest. Review number 4, extreme value theorem. This theorem guarantees maximum and a minimum exists under some conditions. This theorem says that a function that is continuous on a closed interval must have a maximum value and a minimum value on the interval. Review number 5. A point C in the domain of a function. The domain of a function is the set of all x values where function values are computable. A point in the domain of a function at which derivative is 0, tangent line is horizontal, that means, or derivative doesn't exist. When a curve has a corner, derivative doesn't exist. So geometrically, in geometrical language, this says that a point in the domain of a function at which tangent line is horizontal or the graph of the function has a corner, then the point C is called a critical point of the function. From this definition, we can see that there are 2 types of critical points. One is where derivative is 0. The other type is where derivative doesn't exist. Review number 6. This is an observation. Suppose a function is continuous on a closed interval. According to extreme value theorem, this function must have a maximum value and a minimum value. If you draw a continuous curve over some closed interval, then you will see that maximum value and minimum value can only appear at the following points. They cannot appear at other points. Maximum and minimum, or the highest or the lowest point of the graph, can appear at m points of the interval. Possible. Also, they can appear at a critical point inside the interval. This is an open interval. Inside open interval, that means that between the two endpoints, A, B. Maximum and minimum can appear at a critical point. According to the definition of a critical point, that means that maximum and minimum can appear at a point where tangent line is horizontal, or there is a corner there. Based on this observation, then we can develop 3 steps to locate maximum and minimum of a function. This is review number 7. To find the maximum and minimum values of a continuous function on a closed interval. Again, continuous function on a closed interval is guaranteed to have maximum and minimum on the interval. Now, how to find the maximum and minimum over this interval? From this observation, we see that maximum and minimum can appear at critical points. So, step 1, we find all the critical points inside the interval. Then, step 2, compute function values at these critical points. Because maximum and minimum can also appear at endpoints, so we also compute function value at the endpoints. Step 3, now we can make conclusion. The largest function value in step 2 is the maximum function value of the function on this closed interval. And the smallest function value in step B is the minimum function value of the function f over this interval, AB. In the following, let me show you examples about how to use these 3 steps to solve problems. Example 1. Find the absolute maximum and minimum values of this polynomial over this interval. Here is the graph of the polynomial. But we don't consider the whole graph of the polynomial. We only consider the portion over the interval. That means that this portion starting at this solid point and ends at this solid point. We only consider this portion of the graph. And we want to find the highest point of this portion and the lowest point of this portion. We use the closed interval method in review number 7. Step 1, there are 3 steps. Step 1, find all the critical points inside the given interval. 5 critical points. So we compute derivative first. This is the derivative of the function. Then set the derivative to 0 and solve the equation to obtain critical points. The solution of this equation are 0, 1, and 3. All these 3 solutions are inside this interval. So inside this interval, there are 3 critical points. Step 2 of the closed interval method. Compute function values at critical points and also at endpoints. The function value at left endpoint, -1 is left endpoint. Plug in -1 into the function. Then we get function value at -1 is 37. Yeah, -1 here, 37. Yeah, the height of this solid point is 37. Similarly, function value at 0, plug in 0 in the function. Then we get function value is 0. Function value is 0. Yeah, this one here. Function value at 1, plug in 1 in x. Then we get function value at 1 is 5. 1 is about here. Function value at 3, the third critical point is -27. Function value at 4, 4 is the right end point of this interval. Function value at 4 is 32. Now, step number 3 of the closed interval method. The largest function values in step 2, 37, 0, 5, 27, 32. The largest is 37. So this is the maximum function value of the function over this interval. The absolute maximum value is 37. Where when at -1, when x is -1, function value is the largest. Yeah, that means that this point here. This point is the highest point of this portion of the graph of this polynomial. The smallest function value in step 2, 37, 0, 5, -27, and 32. The smallest is -27. So the absolute minimum value is -27, where when x is free, function value is -27. So this is the lowest point of the portion. Yeah, this portion, the lowest point is here. Yeah, the location is x is free, and the function value at this point is -27. So the function over this interval, the smallest function value is this. The largest function value is this. Second example. Find the absolute maximum and minimum values of this function on this interval. Again, this function is defined from negative infinity to positive infinity. So this function has graph everywhere. But we don't consider the whole graph. We only consider the graph over this interval. That means that from this solid point to this solid point, only consider this portion of the graph. And we want to find the highest point of this portion and the lowest point of this portion. We use the closed interval method in review number 7 to solve this problem. Step 1, find all interior critical points. Find all critical points inside this interval. To find critical points, compute derivative first. To compute the derivative of this function, you can use product formula. But I prefer to use quotient formula because I can write this function into a quotient here. So I use quotient formula. Derivative is derivative on the numerator times denominator minus numerator times derivative on denominator, and then all divided by denominator square. This is quotient formula. Derivative of the power function x to the third is 3 times x squared. Derivative on ex is ex. Now, let me factor out ex from the numerator and cancel it from the top and the bottom. The bottom has 2 ex, so I can cancel 1 ex. And take x squared out, then I get this. Now, set derivative to 0 and solve for x to get critical points. The critical point is 0. When x is 0, derivative is 0. When x is 3, derivative is 0. So there are 2 critical points. Step 2. Compute function values at the critical points and also at endpoints. Function value at 0, plug in 0 in x here. Then to get function value is 0. So when x is 0, function value is 0. This is the graph of this function. Similarly, plug in number 3 in x, then we get function value is this. Plug in -1. -1 is the left endpoint of the interval. Plug in -1 in x, then we get function value is this. Plug in 5. 5 is the right endpoint of the interval. Then we get function value is this. Okay, now step 3, make conclusion. We have 1, 2, 3, 4. 4 function values in step 2. The largest function value is here, is this, yeah. So the absolute maximum value of this function over this interval is 1.3443. The location is x is 3, about here. Yeah, the highest point, about here. Yeah, the x value is 3. Of these 4 function values, the smallest one is this. So the function The minimum value of this function over this interval is this number, where the location is x is -1. Here, yeah, this point is the lowest point of this portion. The highest point is here. The location is 3. The lowest point, the location is -1. The next two examples are about finding critical points. Take a review about what is a critical point. Go back to the review. A critical point is a point in the domain of the function at which derivative is 0 or doesn't exist. This is the definition of a critical point. Okay, now go back to the examples. Example number 3 today. Find all the critical points of this function. So a critical point, because a critical point is a point where derivative is 0 or doesn't exist. Let's compute derivative first. It is a quotient, so we use quotient rule to compute the derivative. By quotient rule, derivative on the numerator times denominator minus numerator times derivative on the denominator, then all divided by denominator square. Derivative on x minus 1 is 1. Derivative on x squared minus x plus 1 is 2x minus 1. Now, simplify the numerator. Then we get this. And distribute this negative sign. And further simplify the numerator, then we get this. This is the derivative of the function. Okay, now we can find critical points. Critical points, there are two types of critical points. One is derivative doesn't exist. The derivative has a denominator. So when denominator is 0, derivative doesn't exist. So I first set denominator to 0 and solve this equation. Take square root on the both sides, then I get this. Then by quadratic formula, I get this. Under this square root, the number is negative, so no real solutions. That means that there is no critical point can make derivative doesn't exist because a low solution, no real solution. Calculus, all the solution, all the numbers are real numbers. Calculus only consider real numbers. So no critical point where derivative doesn't exist. Okay, now next, I set derivative to 0. I set derivative to 0. Here, I have a typo. This should be g derivative. Set derivative to 0 and solve this equation. Move the denominator to the right-hand side. Then I get this equation. Factor x out, then we can see that the solutions are 0 and 2. So critical points of this function are 0 and 2. At these 2 points, derivatives are 0. So this function has two critical points, 0 and 2. Example number 4 today. Find all the critical points of this function. Okay. Now compute derivative first. Take derivative on the function. By difference rule, the function is a difference, right? 1 over x minus lateral log of x, difference rule. 1 over x derivative, you can use quotient rule to get derivative is this. Lateral log derivative is 1 over x. So this is the derivative of this function. Okay, a critical point is a point where derivative doesn't exist or derivative is 0. Where derivative doesn't exist, clearly when x is 0, derivative doesn't exist. Derivative doesn't exist at 0. But 0 is not in the domain of the function. When you plug in 0 into the original function, log computable. 1 over 0, log computable. Lateral log of 0, log computable. So 0 is not a critical point of this function because this point is not in the domain of the function. Okay, next, we set derivative to 0 and solve. Derivative is 0, solve this equation to get a second type of critical points. Critical points, there are 2 times critical points. Now I need to solve this equation. Multiply -1 to the both sides. Then I get this. To eliminate the denominators, I multiply the left-hand side by x squared. Multiply the right-hand side by x squared. Then distribution. Left-hand side is 1 plus x. Right-hand side is 0 times x squared is 0. So I get 1 point, 1 solution, -1. So when x is -1, when x is -1, derivative is 0. So this is a critical point. But again, -1 is not in the domain of the function f. When you plug in -1 in x here, lateral log of -1, calculator says that log computable. So -1 is not in the domain of the original function. So therefore, -1, yes, it may derivative 0, but it is not in the domain of the function f. So therefore, -1 is not a critical point of the function f. So conclusion, this given function has low critical point.